Okay, welcome back. We're looking at three examples of input-output relationships. I have number one, number two, number three, and for each one, we're going to determine if these systems, characterized by their input-output relationships, are linear and, separately, are they time-invariant. I wanted to save board space, so I did not write out the definitions of these two properties again. So please consult your notes if you have some, or go back to video 2.6 to look up the properties of linearity and time invariance. Okay, so I've got this input-output relationship that says the output is x of twice the time input. So we looked at this a while back. We said what this is doing is compressing the signal by a factor of 2. So we want to know, first of all, is that linear? We'll answer that question. Okay, so if I put in a signal x1 of t, then that would produce a signal we'll call y1 of t. And what is that signal? Well, it's whatever I put in, x1 of 2t. And here the subscripts just mean I'm putting in something particular. I'm almost like doing an experiment, or I'm probing the system. I put in something and then I observe what I get out. So I put in x1 of t and I observe that I get out y1 of t. And then I kind of continue the experiment. I put in a different signal, x2 of t, and I get out what we'll call y2 of t. And of course that is whatever I put in of 2t. Okay, now I make the following experiment. I put in a mixture. So we'll use alpha. So I put in a scaling constant of the first input plus beta, a scaling constant of the second input. So I put a mixture or a linear combination of those two input signals. And I want to know, what do I get out? So we'll call that y3 of t. Okay, what do I get out? Well, according to our system, we scale the time variable by 2, compressing the signal. So wherever there's a t in the input signal, so right here, I'll underline it in red, wherever there's a t in the input signal, I scale it by 2. So this becomes alpha x1 of 2t plus beta x2 of 2t. And then immediately we recognize x1 of 2t, well, that was this here, that was y1 of t. And x2 of 2t, well, that was this was y2 of t. And so we can write this as alpha y1 of t plus beta y2 of t. So I can conclude then, yes, this is linear. And the reason I can conclude that is because we put in a mixture, a linear combination of the two input signals, and what did we get out? We got out the same linear combination, or the same mixture of output signals. That's exactly what it means to be linear. That's a linear system. Okay, and notice we made no assumptions on the inputs. We didn't say anything about, oh, x1 is a sine wave or a unit step or anything like that, or x2 is an impulse, or alpha is 1 and beta is 3 or whatever. We made no assumptions regarding x1, x2, alpha, and beta, and we were able to prove this linearity property. And in order to do that, of course, we cannot make any assumptions, because this must hold for all x1, all x2, all alpha, and all beta. Okay, now we ask the question, is system 1 time invariant? Okay, well, let's say I plug in a signal, x1 of t, and it produces y1 of t, which is x1 of 2t. Okay? Then I input x1 of t minus t0. So I shift it. What do I get out? Well, according to the system, I get out, we'll call it y2 of t. I replace t with 2t. Okay, so I would get x1 of 2t minus t0. Okay, so this is what I get out. And I ask myself, is that y1 of t minus t0? So is that the same shift in the first experiment? Well, if I replace t with t0, so y1 of t minus t0 is x1 of 2 times t minus t0, right? Replace t with t minus t0. This is x1 of 2t minus 2t0. So is that what we got? No. So we conclude that this is not time invariant. Now, if that was a little abstract for you, we can find a counterexample then. Remember, to disprove a property, all we have to do is find a counterexample. So I'll show you a counterexample. I'll show you what all of this means if this is too abstract for you. So, by the way, if that is too abstract for you, you should work on your mathematics and your intuition about these things. Because this class will get abstract at times. Force yourself to draw these pictures that I'm drawing if this is too abstract for you, because I won't always draw these pictures. Okay, let's say we input this is x1 of t. Okay, and we know what we get out. We get out this signal compressed by a factor of 2. We went over that with time transformations. So this becomes 1/2, and this becomes minus 1/2. This is what we're calling y1 of t. Okay, now let's say I put x1 of t, but I delay it by, let's say I delay it by 1 unit. Or let's say I delay it by 2 units, 2 units. So this will be x1 of t minus 2. Okay, what does that look like? Well, the left edge now is at 1, and the right edge now is at 3. This is still 1. Okay, so my t0 in this particular example is 2. Now let's observe what I get out of this system. So when I put this in here, I would get out, call this y2 of t. And according to the system, I get out y2 of t is equal to x, what I put in, scaled by 2. So I would get out x1 of 2t minus 2 with the time scaled by 2. Okay, so I'm replacing the t variable with 2t. That's what the system is doing. So now I'm going to try to find these edges. Well, the original edge occurs, the left edge occurs at minus 1. So what value of t do I have to pick here so that this curly bracket is equal to minus 1? Well, if I pick, let's say 1/2, I think does it, right? If t is equal to 1/2, then inside the parentheses is -1, and then I have x1 of -1. x1 of -1 is this left edge. So in other words, I'm just trying to plot this thing. So if I choose t is equal to 1/2, then I have y2, which I'm trying to plot, of 1/2 is equal to x1 of -1. Okay? Stay with me here. x1 of -1, that's this left edge. So this is telling me that the left edge of the output, y, is occurring at 1/2. So here's 1/2. Okay, now I'm going to repeat this process and try to find where the right edge is. So again, this parentheses, I need the inside the parentheses to be equal to 1, because that's where the right edge occurs in the original signal. So what do I plug in for t to make this 1? And it looks like I plug in 3/2. If t was 3/2, this would be 1. So y2 of 3/2 is equal to x1 of 1. Okay, so x1 of 1 is this right edge, and so this is telling me now that right edge is occurring at 3/2. And so this is what I get out. y2 right here is what I get out when I put in this signal here. Now, we ask ourselves, is y2 a delayed, a shifted version of y1 with the same shift as x1 and x2? You see, this is the idea. So we plugged in x1 and we got y1. Now we delayed x1 by 2 units. So do we get the same delay in y, 2 units? So did we? No. We delayed y by 1 unit, you see. This is y1 of t minus 1 unit because of the compression by 1 unit. So that's exactly what we said over here mathematically. We said that we do not get the same delay back. So this is our counterexample. Okay, so we're going to move on. Feel free to pause the video if you would like. Example 2. So I've got this system here. We want to know, is it linear and is it time invariant? So let's address linearity first. So if I plug in x1 of t, then I get y1 of t, which is t times x1 of t. And if I plug in x2 of t, then I would get y2 of t equals t times x2 of t. And so the question is, if I plug in a mixture of those two signals, do I get the same mixture of the output signals? Okay, so what do I get when I plug this in? Well, according to our system, this system takes the input and just multiplies it by whatever time it is. So here's the input, and I'm going to multiply that by whatever time it is. So this is what the system is doing. Okay, call this y3 of t. So notice I can distribute that t in. So we'll say y3 of t equals alpha times t x1 of t plus beta t x2 of t, like that. And then I identify this as, without the alpha anyway, this is y1 of t, and without the beta, this is y2 of t. And so look at what I have. I have alpha y1 of t plus beta y2 of t. I have the same linear combination in the outputs. And so I can conclude that, yes, this is linear. So is it time invariant? By the way, look at this input-output relationship in 2. Would you expect that to be linear? Maybe not though, but we have to work on our intuition. So this thing is linear because the t here is not x of t, so it's not like a square in the input. Okay, so is this time invariant? Well, if I plug in x1 of t, so some signal, I would get out y1 of t equal to whatever time it is times x1 of t. Now, if I shift that signal, so if I put in x1 of t minus t0, I would get out y2 of t. And so I'm just replacing t with t minus t0 in the input signal. So I would get whatever time it is times x1 of t minus t0. And we ask ourselves, is this, question mark, the previous output delayed by, or shifted by t0? Are those the same things? No, they're not, because if I take y1 of t minus t0, so this is replace all the t's and y with t minus t0, then I get t minus t0 times x1 of t minus t0, and I compare these two things, this thing with this thing, and I say, no, they're not the same. So no, this is not time invariant. It's time varying. And working on our intuition, we can say that it's time varying. You can think of this thing as an amplifier or a proportional block, but the proportionality constant, right, before this was like 2 or 3, the proportionality constant is changing with time. It's t. So at t equals 1, the proportionality is 1. At t equals 2, the proportionality is 2, and so on. So this is like a proportionality block or an amplifier whose proportion is changing with time. So something inside the system is changing with time. So that's not time invariant. No. Okay, moving on. 3, we have a discrete time system. And we want to know first, is that linear? Okay, is this guy linear? And, well, it certainly looks like it's linear, right? mx plus b, but let's check it out. So if I input x1 of n, that gives me y1 of n equals. So this system takes the input, multiplies it by 2, and adds 1. Now if I put in y2 of n, I get out, we'll call it y2 of n, twice what I put in, plus 1. Now observe if I put in alpha x1 of n plus beta x2 of n. What do I get out? Well, again, the system takes twice what I put in, so there's twice what I put in, and then adds 1. So if we distribute that 2 in, like this, And we ask ourselves, is this the same linear combination of the output? So where is there a 2x plus 1 hanging around? No, there's not. Like this guy is 2x plus 1. If I factored out the beta, this is 2x2 plus 1 over beta. And then there's no 1 for this guy. So this is not the same. This is not alpha at y1 plus beta y2. In other words, if I back up, notice this does not equal alpha times 2x1 of n plus 1, right? That's y1 plus beta 2x2 plus 1. That's y2. So these two things are not equal to one another. So this is not linear. No. Okay, and so you should be able to find a counterexample also. So you don't need to prove that if you can find a counterexample. Now, for time invariance, okay, I plug in x1. That gives me y1 of n equals twice what I plugged in plus 1. And now I delay it, or I shift it. I shouldn't say delay, but I shift it. Shift the input. I get twice what I put in plus 1. So is that a delayed y1 of n? So is that question mark y1 of n minus n0? And so we look here. If I replace n with n minus n0 in this equation, do I get this? Yes. Yes, I do. So this is time invariant. Yes.